Welcome to the UGC lecture series. This is the EPG Pathashala lecture series and we are talking about the subject computer science and the paper is machine learning. In the next two modules, this module and the next module, we will be talking about classification and regression trees, which is an important aspect of machine learning in general. So, the development team responsible for the preparation of this module is given here. And now let us look at what are the learning objectives of this module. The first is to explain the CART. Now, CART is classification and regression trees approach to decision tree building, to outline the key features of CART, to explain the various steps in this particular CART approach. We will discuss what is CART in detail later on, and to discuss a recursive partitioning approach and to outline the Gini index. So, these are the basic concepts that we will be covering in this module, and the keywords are classification and regression tree, that is the CART, recursive partitioning, stopping criteria, tree pruning and the Gini index. So, let us look at what is the relation between decision tree and CART. That is the first thing we will have to discuss. So, any decision tree, what does it do? It will successfully split the data into smaller and smaller subsets. This we saw in the last module. So, it will be ideal if all the samples associated with the leaf node are come from the same class. Such a subset or node is considered pure in this case. So, what we are trying to say is all the samples that come at the leaf of the decision tree, if it all belongs to the same class, such a subset is called pure. This we had already discussed as I already. Now, a generic tree growing methodology known as CART successfully splits nodes until they are pure. So, basically a CART is a method of obtaining pure nodes in a decision tree. Okay, it is a tree growing methodology which successfully splits the nodes again and again until you reach the pure subset. Okay. So, the CART approach is as follows. What do we do in this CART approach? So, the first is, as I already told you, it is a classification and regression tree, that is the full form of CART. It is developed by Bridman, Friedman and Alshenstone in the early 80s after decision tree became a little popular. Introduce tree based modeling into the statistical mainstream. So, it is basically use statistics to do this tree based modeling, and it is a rigorous approach which involves cross validation, and it is trying to select the optimal tree at the end. That is the idea. And this C 4.5, it is a machine learning approach by Quinlan, which is also used for this type of decision tree. It is a non-parametric technique using the methodology of tree building. So, what you are trying to do is you are trying to build the tree step by step or grow the tree step by step, and it is a non-parametric technique to do that. So, classifies objects or predicts outcome by selecting from a large number of variables, the most important ones that determine the outcome variable. Now, this we had already discussed in decision tree, I will just recollect that. What we essentially do is we want to predict the outcome. In order to predict the outcome, you have a large number of variables. Now, the idea is you have to choose the important variables that will determine the outcome variable. So, CAT analysis is a form of binary recursive partitioning. Okay. Why binary? Each and every point you partition the node into two halves. Okay, so that is why it is called binary, and you keep partitioning it. You start with all the data sets, then you partition into two, then you take the subtree partitioning into two and keep on doing that till you reach the leaves. So, an example from clinical research. So, this was done by University of California. It was a development of a reliable clinical decision rule to classify new patient into categories after admission for a heart attack. So, you want to divide the patients into categories. So, there are 19 variables which are collected during the first 24 hours of their admission for 215 patients. Of course, we considered those patients who survived the first 24 hours after the admittance into San Diego Hospital. This was the example that was taken. The goal was to check, can the high risk, that is will not survive 30 days, patients be identified. Can the high risk patients be identified so that they can be given special treatment and so on. So, this is the idea, and it is a crucial problem that had to be solved. 19 variables, that is 19 parameters were selected for this, and we considered 215 patients. So, the classification of patients was basically binary classification as high risk and low risk groups. So, we started with the first variable is the minimum systolic blood pressure over initial 24 hours greater than 91. We considered initial 24 hours, is that greater than 91. So, you have only two answers, yes and no, it is a binary variable. If it is no, then it is high risk. If it is yes, then is the age greater than 62.5. If the answer is yes, then you check if sinus tachycardia is present. If it is yes, it is high risk. If it is no, it is low risk. If the age is greater than 62.5, if it is yes, only you go to high risk, otherwise you go to low risk. So, this is a typical example of the classification of patients. If you look at the way in which it is modeled, every point you have only an yes and no answer, and you have a binary partitioning. Okay. Please note what is being partitioned. The data set starts with the whole set, and if the minimum let us assume you have 200, we have said that we have 215 patients. So, out of this 215 patients, maybe 100 have greater than and the rest have lesser than. So, it is divided into two subsets. Then you take this subset and keep on dividing. So, this is the idea. We have seen this again in decision tree before also. So, now let us look at the definition of CART. CART builds classification or regression trees for numerical attributes. If it is numeric attributes, we call that a regression tree. If it is categorical attributes, we call it as classification. So, that is the difference between classification and regression trees, and the model that is used for both are almost similar. Okay. So, the classification tree analysis is when the predicted outcome is the class to which the data belongs. It is actually the class. And regression tree analysis is when the predicted outcome can be considered as a real number. That is, example, the price of a house or the patient's length of stay in a hospital. These are considered as numerical values or real numbers, while for classification trees what you get as output is a categorical variable. For example, in the previous example we saw that high risk and low risk was the categories that we wanted. The term classification regression tree analysis is a term used to refer to both the above procedures, for whether it is for categorical variables or for numeric attributes. The attributes are like that. Both the cases we use the classification regression tree as a common terminology. Trees are used for regression and trees used for classification have some similarities, but they also have some differences. That is, mainly the difference is the procedure of used to determine the split is different in the case of classification tree and regression tree, but there are many similarities also. Okay. Now, let us look at again some key CART factors. Some of the features of why CART has become quite a popular method for doing this type of classification or regression is automatic field selection. So, it actually handles any number of fields and it will automatically select the relevant fields. We will come to how this is done later. We are just saying, so automatic field selection is an important aspect or feature of CART. Then no data pre-processing is needed. This is a very, very important criteria or feature of CART. It does not require any kind of variable transforms and it is impervious to outliers. This is another important aspect, in the sense that if you have some outliers, it is not going to affect the result as much as it does in other type of techniques. And it is missing value tolerant. So, only there is a moderate loss of accuracy due to missing values. It is not going to affect it very largely. So, these are the main three important criteria which are considered as issues for other techniques. So, this CART was mainly designed to handle these issues: automatic field selection, no pre-processing and tackling of missing values. Now, let us look at the general CART framework. When you talk about the general CART framework, there are 6 questions that come into the picture. The first question is, how many splits will there be at each node? This is the first question. Should the questions be binary? So, do we want it to be split only into 2 or numeric? That is, if the height is greater than 5.4 or multi-valued. That is, for example, cast. So, it could be 3, that is, it could be binary, yes or no. It could be numeric, again treated as binary. So, if it is blood pressure is greater than something, one side and lesser, still binary but numerical values, or it could be multi-valued. So, that is the first decision we have to make. The second decision we have to make, which we also discussed when we were talking about decision tree, is which property should be tested at each and every node. Which property should you test at each node? That is, which is the attribute you will consider first. Now, remember, the overall aim is to keep the depth of the tree or the height of the tree as small as possible. That is the idea. So, which properties or attributes should be tested at each and every node? Then the next very important question is, when does a node become a leaf? Okay. The idea is that when do I stop the splitting? That is the idea. In other words, that is when I reach a leaf node, I don't have to go further down the tree. So, when do I know that a node is a leaf node? The next question is, how pure is a large tree? Remember what the definition of pure? The definition of pure is all the subset will all belong to the same class. So, how, sorry, not how pure, how to prune a large tree. We are talking about that. How to prune a large tree. Given a large tree that you develop, how do we prune it? We will come to this. This is something different we have to talk about. Purity also comes into the picture. That was what we discussed before. If a leaf is impure, how do you assign labels? So, how do we assign labels? See, we cannot say that everything will be pure only. So, if it is impure, how do we assign the labels? And the next question is, how we have already told in the last slide that it handles missing values. So, how to handle the missing values? So, these are the main questions. One is how many splits do we do? Number of splits. Then which are the attributes you should test at each and every node? Then when does a node become a leaf? That is when to stop the partitioning. Then given a large tree, how to prune it? We will come into that pruning aspects later. Then if a leaf node stops the partitioning, how to assign the labels and how to handle missing data. So, these are the 6 basic questions of a CART framework. Now, let us look at the steps. The steps is initialization. Create a tree with one node that contains all the training data. So, whatever the training data, everything together is put in one node, that is the initialization part. The second step is tree growing or recursive partitioning. That is, you have a large data set, you keep on dividing the data set, that is recursive partitioning. So, for doing recursive partitioning, there are some steps. The first step is select a splitting criterion. How do you split the data set? Basically, you are splitting the data set. How do you split the data set into 2? So, for that we are now, you remember that this is a tree modeling technique based on statistical methods. So, you use likelihood. What is the likelihood? Find the best question for splitting each terminal node. Split the one terminal node that results in the greatest increase in the likelihood. So, the greatest increase in likelihood is what you will use for selecting the node for splitting. So, you will select the terminal node that gives you the greatest likelihood. Then given that, you select the best split in the variable in terms of the reduction in impurity. That means what you do, you rank all the best splits. Suppose you have more than one best split, you rank all of them. After that, how do you select? You select it in terms of the reduction in impurity. Remember, our aim is to get as many pure nodes as possible. So, you try to select in such a way that the impurity is reduced. So, that is the next one. Then you have tree growing. So, recursive partitioning, that is the continuation of that second step. And the next component of tree growing is assign the predicted classes to the nodes according to the rule that minimizes misclassification costs. Now, we have brought in 2 terms. One is the increase in likelihood and the second term that we have brought in is misclassification cost. So, we want to minimize misclassification costs. So, according to that, you have to predict the classes. And finally, we have something called the stopping criteria. How far do we grow? When do we know that we have to stop the partitioning? Stopping if each leaf node contains data samples from the same class or some preset threshold is not satisfied, you stop, otherwise continue growing. So, the idea is splitting, growing or splitting. The idea here is when do you stop? One is if the particular node that you have is pure, then there is no question. Otherwise, you have reached a threshold and a preset threshold, and if it is not satisfied, that is if it may be cost or whatever, if it is not satisfied, you stop, otherwise you split. It could be either way. So, some threshold you put. So, these are the 4 steps in, we have some more steps in recursive partitioning. Then you have again the 5th step, how to tackle the missing values. Now, what you do, use surrogates program which uses the best available information to replace the missing data. So, you based on the variable that is relative to the outcome variable, you try to put a surrogate program that will replace some information to replace the missing value. So, that is how you do recursive partitioning. So, what you start, you do an initialization, then you do recursive partitioning. This recursive partitioning, you have certain 5 sub steps. One important one is how do you stop, when do you stop, how do you label, how do you tackle missing values, all that we consider. Now we have to stop the tree building. When every aspect of the data set is visible in the decision tree, then you stop the tree building. Okay. Now you have, now what is the first step we did? We did initialization, we did recursive partitioning. So, you keep recursive partitioning, in other words, is nothing but building the tree. Okay. So, then you stop building the tree. After that, you have got a large tree, you have to do pruning. Pruning means cutting away certain parts of the trees such that you do not have to consider them. Use an independent test or cross validation to prune the tree, and use an independent test set to prune the tree. So, trimming off parts of the tree, that does not work. So, that is what you are essentially doing with pruning. Ordering the nodes of a large tree by contribution to tree accuracy, which nodes come off first. So, that is one way of pruning. So, you order the nodes of a large tree by contribution to the accuracy of the tree, and accordingly you prune off that contributes the least. And then you have the optimal tree selection. So, the best tree that fits the data set with a low percentage of error is the best one. So, deciding on the best trees after growing and pruning is what we do. You have to balance simplicity with accuracy. The more larger the tree, the more accurate it is, but the more accurate it is and the larger the tree is, it is not as simple as it is to find the class. So, these are the two criterion you will do together to get the best tree. So, the key idea behind all this is the growing of the tree or the recursive partitioning, as we have already discussed. So, take all your data, consider all possible values of all the variables, that is what we do. So, consider all possible values of all the variables. So, for example, suppose I have, let us assume binary, or it could be multi-valued, let us take binary. Then if you have 4 variables, you will have, each will have 2 values. So, that is the idea. Then select the variable or value x is equal to t1 that produces the greatest separation in the target data set. So, what you have to do? You have to take the data and choose a variable such that you get the greatest separation. What is the meaning of greatest separation? Your output class is already known to you. So, when you choose one variable, it will give you mixed. If it gives you greatest separation between the two classes, then you take that variable, and that is called a split. If x is less than t1, then send the data to the left. T1 is the value and x is the variable. Variable is x and the value is t1. If it is less than t1, you send it to the left. If it is greater than t1, send it to the right. So, that is the, we are assuming binary. Now, repeat this process for the 2 nodes that you have got. So, you have got one. Now, what you start with the whole data set, you split it into those with x less than t1 and those with x greater than t1. Now, this is now a new data set, x is less than t1, that you take and you keep splitting it into 2 nodes at each stage. So, you get a tree. Now, according to our thing, we are assuming whatever the values, whether it is numerical or whatever it is, we are assuming binary split. So, at each and every point it is less than t1, greater than t1, like that we will do. Okay. So, the steps of recursive partitioning is pick one of the predictor variables x1, pick a value of x1, say s1, that divides the training set into 2, not necessarily equal portions. Okay. Measure how pure or homogeneous each of the resulting portions are. That is, you have 2 subsets, you find out how pure it is. You remember the definition of pure. What is the definition of pure? Pure told us that all the values or all the points in that particular subset belongs to the same class. So, then you call that as pure. So, you measure how pure or homogeneous each of the resulting portions are. Pure are containing nodes of mostly only one class. Algorithm tries different values of x1 and s1. I will come to this in detail. x1 is the attribute and s1 is the value. So, last time we took t1, you could have taken t2, you could have taken t3. So, you have to choose the variable as well as the value at which you will split the data for that the value of that particular variable, so that you maximize the purity in the initial split. After you get a maximum purity split, then you repeat the process for the second split and keep on doing this till you reach the leaf. Okay. So, what are the features of card? Again, data split into 2 partition, binary split. Splits are based only on one variable. Okay. You take one variable at a time and split it. And partition can also be split into sub partitions, hence procedure is called recursive. And card tree is generated by recursive partitioning of the data set. So, parent gets 2 children, each child produces 2 grandchildren, 4 grandchildren will produce 8 great grandchildren, and so on. So, how do you construct a tree? Selection of the splits is important. Decisions of when to decide that a node is a terminal node, when we have reached a leaf node, that is, we do not want to split further. Assigning a class to each terminal node. Once you have reached the terminal node or the leaf, you have to decide what is the class you want to put for that. the steps of tree building start with splitting a variable at all of its split points. What is the split points? All the values that it has. Sample splits into 2 binary nodes of each split point. Select the best split in the variable in terms of the reduction impurity. Please note, I am taking, first I am selecting a variable. Once I have selected a variable, I am selecting where to split the variable. So, suppose the variable has a value ranging from say 30 to 70. I could split at 40, I could split at 50, I could split at 60. So, each of those I will take and I will try to find the, when I split I will get into 2 subsets. I will try to find the purity of each of the subsets, and depending upon the best split for that particular variable is decided by the reduction in purity. So, I have initially one purity, if it is less than that, that is the split I will choose. So, you repeat the steps 1 and 2 for all the variables. Now, I have done it for one variable. Say suppose I have 19 variables, each of the 19 variables will have different split points, and I will repeat the steps 1 and 2 for each of the variables. Now, what you do? You rank all the best splits. So, that is, for one variable you will have the best split, and you will have say 19 variables, you will have 19 best splits, that is the best split for each variable. Okay. And then of these 19, choose the one which has the best split. So, you rank all the best split and select the variable that achieves the highest purity at the root. So, whichever gives you the highest purity, that you select. Now, assign classes to the nodes according to a rule that minimize misclassification cost. We have already discussed this. So, you have to assign classes to the nodes depending upon the minimization. Now, you repeat step 1 to 5 for each non-terminal node. Now, when you finish this, you will have terminal and non-terminal nodes. So, now you select the non-terminal node and repeat all the steps. So, you will grow a very large tree called T max until all terminal nodes are either small or pure or contain identical measurement vectors. Prune and choose the tree using cross validation. So, how do we split? So, order records according to one variable. Find midpoints between successive values, divide the records, and after evaluating that split, try the next midpoint. This is for one variable. Remember, we have to try this for each and every variable. Now, let us take categorical variables. Examine all possible ways in which the categories can be split. Categories A, B and C can be split in 3 ways. You can have A and BC as one split, B and AC as another split, and C and AB as another split. So, this is an example of a simple category ABC split. With many categories, the number of splits become very, very large. So, every split point you have, you can try any number of split points, right. So, many tools support only binary categorical variables. So, in that case, the limit on the number of splits that is possible. Now, how to split? Let us take this example. You have car type, age, child, and you are going to get the output is yes or no. That is what we are having. Now, if you take the car type, you could have split using car type, using age or using child, one of the variables you could have chosen. Here is chosen age. Now, once you choose age, the age varies from some particular value, say 25 to some particular values. Now, here in this particular one, we have chosen less than 30 and greater than 30. So, the split point we have chosen is 30. That is what the meaning of split point for the variable age. Once you finish that less than 30, you have now all the nodes, this particular data set will be split into nodes that have, all the data that have less than or equal to 30 and all the data that have greater than 30. The others it does not bother. So, now I have one set. In that set I have to choose. So, I can choose car type or child. I choose car type. In car type, I could have chosen, is it a sedan? Is it it's a binary one only. So, you have only 2. So, there is no question of that. So, either it could be sedan or it could be sports truck. So, according to that I do. Now, if you take number of child in the greater than 30, I take number of child as my split point. So, again there I could have had, I have 0, 1, 2, I could have chosen 0 and greater than 0, or I could have chosen less than 1 and greater than, less than or equal to 1 and greater than 1, or I could have chosen 2 and lesser than 2. So, it could depend on how I do the split point. And according to that, if I take 0, then again I try car type. If it is greater than 0, I try car type and I get yes and no as answers. So, this is a tree that I have built using the property of cart. That is, I am doing recursive partitioning, I am choosing the variable, I am choosing the split point. So, let us take an insurance example again. Suppose you have 3 variables, vehicles, number of vehicles is 1 to something, and age category 1, 2, 3 to 6, and liability 0, 1. So, I have 3 variables, each I am having these values. So, at each iteration cart will test for 15 tests, vehicle less than 3, vehicle less than 2, vehicle less than 10, age less than 2, age less than 6, liability less than 1. So, like this the split points are changing. So, select split resulting in greatest increase in purity. So, at the node I am selecting it into to form two subsets. So, perfect purity means each split will have all claims or all known claims. Perfect impurity means each split will have the same proportion of claims and known claims. So, that is the two extremes. You have to go towards perfect purity. So, select the variable value that produces the greatest separation in the target value. That separation means defined in many ways. So, you can define it in many ways. In regression tree use sum of squares errors, we will come to this later, we are not discussing that here. In categorical target, that is classification trees, the choice of entropy, Gini measure or Turing splitting rule is used. We will come into detail about this. So, how do you decide on the separation or the purity of the subset? So, tree based modeling for discrete target variable. In contrast with regression trees, various measures of purity are used. So, there are different measures that are used. They are mostly in regression trees, sum of squared errors only used. In classification trees, some use entropy, some use Gini measure, some use Turing splitting rule. Intuition and ideal retention model will produce nodes that contain either defectors or only non-defectors only. So, we want completely pure nodes, that is our aim. Talk a little more about the splitting criteria. Gini is the purity of a node, P into 1 minus P, where P is the relative frequency of defectors and entropy of a node is the summation of this P log P minus P into log P plus 1 minus P log of 1 minus P. So, maximum entropy or Gini will be when P is equal to 0.5 and minimum entropy or Gini value will be when P is equal to 0 or 1. So, this is the idea. So, Gini might produce small, it will produce small but pure nodes. So, Turing rule strikes a balance between purity and creating equal size nodes. Now, I brought in a new criterion. The new criterion is that my size of the nodes I did not consider, I wanted pure nodes, that is all. But now we are also considering, if I have, let us assume I have a node of 20 and I want to split it, I want only pure. So, here I have 2 nodes and here I have 80 nodes, this is not a very good split. I would preferably like it to be 10 and 10, but then the 10 and 10 should be pure. So, I want both. So, this Turing rule is one method that strikes a balance between these two. So, impurity and recursive partitioning, you select the split that most decreases the Gini index, done over all possible places for a split, that is what this places means, split point. All possible variables also you have to do. So, you take one variable, all split points, all variables and each and every one you will take all the split points. Now, chosen split points become nodes of the new tree. Keep splitting until the terminal nodes have very few cases or all are pure. So, best approach is to grow a larger tree than required and prune it. So, what is the impurity of a node? Now, to do this we need to have a measure of the impurity of a node to help to decide how to split a node or which node to split. So, the measure should be at the maximum when node is equally divided among all the classes. The impurity should be 0 if the node is all in one class, that is what we want. So, there are different measures of impurity, misclassification rate, which is not normally used. No split improves the misclassification rate. Misclassification rate can be equal when one option is clearly better than the other option, or you use information or entropy, and that is basically the basis of what we use, and then we discuss Gini index. So, information on entropy is if a node has a proportion P j of each of the classes, then the information entropy is given as I of P j is equal to summation of P j log P j, where P plus that P1, P2 to Pn minus P is the proportion of cases out of M that belong to class K. Entropy ranges between 0, most pure, and log 2 M, equal representation of classes. That is the range that we have. Gini index is widely used, and this is the one that is used to measure the impurity by cart, and this is given by, it is a modification of the entropy. P is the proportion of cases that belong to class K, and I of P is equal to 0 when all cases belong to the same class, and maximum value when all classes are equally represented. That is, in a subset you have 50% belonging to one positive class and the 50% belonging to the negative class. That is not what you want. You want it to be 0, that is, you want every case to belong, all the cases to belong to the same class. So, this is the way it is discussed. So, tree impurity, we also spoke about tree impurity. Tree impurity of a tree is sum of all the terminal nodes of the impurity of a node multiplied the proportion of cases that reach that node in the tree. So, impurity of a tree with one single node with both A and B having 400 cases using the Gini index, the proportion of the two cases is 0.5, then the Gini index will also be 0.5. So, this is how the tree impurity calculations are done. Number of classes A and B is 400, proportion is 0.5, 0.5, the Gini index also is 0.5 using the formula given in the previous slides. So, this is the number of cases for different cases. You can see that the contribution, the Gini index is 0.375, then the contribution to the tree is 0.1875. When the contribution Gini index is 0.4444, the contribution to the C is 0.33. When it is 0, this is 0. So, this is different values of Gini index. So, split points become nodes of a tree, circles with split value in center. Rectangle actually represent the terminal nodes, terminal points, no further split is possible. Number of lines between nodes indicate the number of cases that we consider. Read down the tree to derive the rule. So, now the next question is how to determine the leaf node label. Each leaf node label is determined by voting of the records within it and by the cutoff value. So, for example, records within each leaf node are from the training data after all. Okay. So, suppose I have let us say some x number, and if the cutoff is 0.5, that means the leaf nodes majority belong to the, the most of the data belong to the majority class. Cutoff 0.75 requires the majority 75% or more has 1 records in the leaf if you want to label it as 1. So, that is the way so you have a cutoff and you vote. So, what have we covered in this particular module on classification and regression trees or CART is the how to do decision tree building using CART. We outlined some of the key features of CART. We explained the various steps of the CART approach and discussed the recursive partitioning approach in detail. Just outline what the Gini index is. Okay. Thank you.